Welcome back to Triptych Algebra. Today's lesson is about everything fractions. Fractions are a super important concept in mathematics up through higher level mathematics. In calculus, if you don't understand the concept of fractions, you're out of luck. But we're going to spend a lot of time talking about them today and making sure we understand why we do the things that we do with them. The numerator is the number on top. It's a 3. The denominator is the 4. The numerator on top is telling you the number of things that you have. It's the numeration. The denominator on the bottom is the type of fraction that you're dealing with. This is important, especially when you're adding or subtracting fractions. If you're thinking of 3/4, you can think of a pi as being 1. The 4 tells you how many ways you split up this pi, so we're going to split this into 4 even pieces. The numerator on top, the 3, tells us how many of these that we have. So let's take 3 of those 4 pieces. That's 3/4 of 1. Before we get going in the nitty-gritty of the operations of fractions, I want to make it very, very clear before we start. Addition and subtraction of fractions or anything in mathematics is very different than multiplication and division. The most important thing as we move forward is don't confuse the two worlds. When we add or subtract, we have a separate set of rules that we use than when we multiply or divide. Generally speaking, is that multiplication and division, the arithmetic of those moves is easier than addition and subtraction, specifically because every time we add or we subtract two things in all of mathematics in the real world, if we want to add them together, they have to be of the same type. Quick example, if I'm going to add 5 centimeters and 3 inches together, the first thing I need to do is convert one of them either into inches or into centimeters so they're both of the same units. That same holds true here. When we multiply or divide, we don't have those same issues, and we'll talk about that. But generally speaking, a different set of rules for addition and subtraction there is for multiplication and division. Multiplication and division are generally easier. Addition and subtraction are generally more difficult. All right, let's tackle addition first. And again, addition is going to be exactly the same process of subtraction. That's always the case with any kind of arithmetic or algebraic structures. In this case, we want to add 3/4 and 1/2. All right, here we have quick visual representations of 3/4. I've cut this pie into 4 pieces. I've chosen 3 of them, and 1/2. I cut it in half and taken one of those 2 pieces right there. If I'm going to add these amounts together, the question becomes, how much do I have all together? Importantly, if I'm going to add them together in any useful way, they have to be measured exactly the same. I'm going to convert the 1/2 into fourths. I'm going to show that visually, and then I'll show you the mathematics of doing that right here. If I cut this pie now into 4 pieces, the question is, how many of those 4 do I have? I have 2/4. If I am now going to add these together, I have 1, 2, 3, 4, 5. I have 5/4. How we do that in practice is we're going to change these so they're the same type. We want to change the halves into fourths. How we do that is we're going to multiply the numerator and the denominator by 2. This is called the fundamental principle of fractions. This is always how we convert fractions. If I do this, what I'm going to get is 3/4 plus 2/4. Now that my fractions are of the same type, specifically fourths, I can add their numerations together. I have 3 of these fourths. I'm adding 2 more fourths to it. Altogether, I have 5 of those fourths. People often get confused on why do I add just the numerators and not the denominators too. It's because they're vastly different things. The number on the bottom, you would never add these together because these are the type of fractions that you have. These have to be identical in order to interact the numerators together. To help you understand this real fast, let's think about a situation right here. I'm trying to add $120 US and 10,000 Japanese yen. I can't add these together. One's in US dollars and one's in yen. Very importantly, the US dollars is the denomination. The 120 is what I would call the numeration. This is how many of this type I have. If these are of different types, I can't add them together. Now, if I convert one or both of them into a shared denomination, then I can add those together. This 10,000 Japanese yen, and I translate that into, or I convert that into US dollars, 10,000 Japanese yen is the same right now as 94 US dollars. If I take that, now that they have the same denominator or denomination, specifically US dollars, I can add their numerators together. 120 plus 94 is 214. I don't have double US dollars. I don't add those types together, just like I don't add the fourths together. All right, let's look at a little bit more complicated example and expand this concept. Now, we know to add or subtract fractions, we have to be of the same type. How do we do that? We're going to use the fundamental principle of fractions. To change a fraction, you can multiply the numerator and the denominator by the same factor, this k in this case right here. What we're going to do is we're going to multiply this fraction, the numerator and denominator, by a common factor, and this fraction by a different common factor in order to make the denominators the same. I'm going to show you how I do that. Then I'm going to talk a little bit about how I found that least common denominator. I'm going to multiply this fraction in the numerator and denominator by 5. And I'm going to multiply this fraction in the numerator and denominator by 4. If I do that, these two fractions, equivalent versions, but with new denominators, you can think of this as like the conversion rate, right? Between different denominations of money or something like that. These are the conversion rates that I'm using, translating now from tenths into 40ths. This will become 28 40ths. Over here, I have minus now 15 40ths. The question may be, how did I come up with the number 40ths? Well, there's a lot of different ways for finding the least common denominator. All over the internet, just Google LCD of fractions or least common denominator. There's a bunch of different techniques. Some of my favorite include like prime factorization or techniques like that. My absolute favorite way of doing this is simply taking the larger of these two numbers. Now I'm trying to find, in this case, a side venture. I'm taking the LCD, or the least common multiples, what we would say, of 8 and 10. What I do is I'm going to take the larger number and start writing multiples of it. So just adding 10 to itself over and over. As I'm doing this, every time I write a new number, I think, hey, does 8 divide that number nicely? So far, 8 doesn't divide 10, it doesn't divide 20, it doesn't divide 30. Now, if I go another multiple of 10, 40, here we go. 8 does divide 40 nicely. 40 divided by 8 is 5. Once I find a number that is divisible by the smaller of the two fractions, this is my least common denominator that I'm going to use. Just to finish this up, we've done all the work. We've made our type the same. They're both 40ths. All we need to do is interact the numerators, 28 40ths, and take away 15 40ths, leaves me with 13 40ths. Just to put a button on adding and subtracting fractions, we always have to have a common denominator. There's a lot of different ways of finding a common denominator. Once we have a common denominator, we only interact, which means add or subtract the numerators. We keep that shared denominator. That concept is the same throughout all of mathematics, even with algebraic fractions that we call rational expressions. All right, let's now multiply two fractions together. Multiplying and dividing fractions is so much easier than adding and subtracting fractions. It has nothing to do with common denominators. In fact, to multiply two fractions is exactly what you'd want to do. Remember, radically different than adding or subtracting. What we do when we multiply two fractions together is simply multiply the numerators and multiply the denominators together. It's as easy as that. 1 times 3 is 3. 2 times 4 is 8. This is the result of multiplying those two together. Let's take a quick second to figure out why the heck can we do this? Again, it's not necessarily we have to always think about the reasoning, but for me, it helps to understand, why can I do this? If you explain that I have to have common denominators and gave me reasons, why can I just multiply straight across? First of all, what does 1/2 times 3/4 mean in a real world context? One way of thinking about it is 1/2 of 3/4. This is important. I'm thinking as 3/4 here as a thing. This is again the denominator and the numerator. And I'm thinking as 1/2 as this multiple or scalar of this amount right here. All right, here we have 3/4. I've taken this box that I'm going to call 1, and I'm split it into 4 different parts. That's the fourths, and I've taken 3 of them. What I want now is to describe what does it mean to have half of those 3/4. So let's take this, let's cut this in half, and now the question is, how much of the original whole do I have? Well, I need to count with size of these pieces. How many of these little rectangle pieces are in the big rectangle? If I continue out this line right here, I can count the types. So this is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 pieces. And I've colored in 3 of those, or I've chosen 3 of those pieces. Is a half of 3/4. When you cut the 3/4 in half, you actually are now dealing with 8ths. And that's the visual right here. I have my big fourths. I cut them in half. Now I have 8ths. Every little block is an 1/8 of that. And I end up with 3 of those 8ths. All right, let's just do one more, little more complicated example of multiplying so I can show you the really cool trick of cross-canceling. We're going to multiply these 2 across, then I need to always make sure I simplify. So 8/9 times 15/14. If I multiply straight across, 8 times 15 is 120. 9 times 14 is 126. That's the multiplication. I always want to reduce. I reduce fractions by going backwards with the fundamental principle of fractions, meaning I can cancel any common factors. In other words, I can divide these both by the same number. It's the same as pulling off a factor. I can divide this and these both by 2. So I will do that now. I'm going to get 60 over 63. And then what I can do is divide those both by 3 to get 20 over 21. Not a big deal. The question is there a way, if you can think about these numbers getting bigger, this is going to get pretty dang hard and could take a long time to reduce. Is there a way that I can reduce quicker and easier? And the answer is yes. You can actually cancel the common factors before you multiply these together, and it makes your life a heck of a lot easier. What I'm going to do is I'm going to look at these 2 fractions and see if there's any common factor between any numerator and any denominator. In this right here, for instance, the 15 and the 9 both can be divided by 3. In fact, that is the same 3 that I canceled right here between these 2 moves. Why these could be divided by 3 is the same reason that these could be divided by 3. I'm going to do that right now. Actually, before I multiply, cancel this factor of 3. That divided by 3 is a 5. 9 divided by 3 is 3. And now what I can do is actually cancel a common factor of 2 between the 8 and the 14. And again, this is important. That factor of 2 is the same factor of 2 that I divided from here to here. Again, I'm canceling a factor of 3 and a factor of 2, as I did in that problem, but while the numbers are still smaller. If I divide this by 2, I'll get a 7. The 8 by the 2 gives me a 4. Now, if I multiply straight across, 4 times 5 is 20. 3 times 7 is 21. Right, now let's talk about division of fractions. To divide 2 fractions, what I'm going to do is flip the divisor and then multiply. This is very, very similar to multiplication, except I have to flip the second fraction, which is the divisor. 9/8 times 4/3. Now that it's multiplication, I employ all the other tricks I had from previously. In this case right here, I can cancel a common factor of 3 between the 9 and the 3. 3 divided by 3 is a 1. 9 divided by 3 is 3. Between the 8 and the 4, I can cancel a common factor of 4 to get a 1 over 2. Now multiplying the resulting numerators and denominators together to get 3/2. Before I explain why you can do this, it's really important to remember throughout all of mathematics, especially when solving equations, to divide by a fraction, to divide by 3/4, is the same as multiplying by 4/3 or its reciprocal. I simply flip the fraction over, replace the numerator and the denominator with each other, and multiply. Let's finish with a quick conversation on why. Why can we flip and multiply with a fraction in order to divide? Before we get there, we need to understand what is division. Division, by definition, is the inverse operation of multiplication. I have a couple different statements right here that I want to talk about. If you take 5, you add 6 and subtract 6, by the definition of addition and subtraction, you must end up back at 5. The same things with multiplication and division. If I multiply the number by 3 and then divide by 3 again, I will always result in the original number. That's a fundamental property of multiplication, division, and addition and subtraction as inverse operations of each other. Let's now use that and the discussion we've had about fraction operations. In this case right here, if I take 2/3, if I multiply it by 4/7 and then divide by 4/7, exactly the same thing should happen. I should end up at 2/3. The question is, does then, if I replace this division of 4/7 by multiplication of 7/4, it's reciprocal, do I end up back at 2/3? And the answer is yes, and it's pretty easy to see. If before I multiply, I do my cross canceling like I'm allowed to, because I flipped these fractions, there's actually perfect canceling going on. I can cancel that 4 and that 4, and that 7 and that 7. In the end, the action of multiplying by 4/7 and multiplying then by 7/4, they cancel each other out as they should with multiplication and division. The resulting expression, as it should, ends up in 2/3. Thus concludes the triptych algebra explanation of fractions. Thanks for playing.